Hi, everyone, and welcome back to part 16 of our Block 74 Apollo Guidance Computer project video. Today, we're going to wrap up the S register in part 3, where we're going to talk about the fixed bank and the fixed extension or super bank register that are used to access the various um, fixed or ROM memory within the Apollo Guidance Computer. Um, One thing I realized on the last episode that I kept referring to the RAM or the erasable memory as core rope, which is actually incorrect. I actually realized it halfway through the video. It is core memory, but it's a dynamic core memory that's the Apollo Guidance Computer used for its erasable memory, and for its fixed memory, it actually used core rope memory, which is almost a literally weaving the data into the memory structure itself through the actual ferrite cores that were used to actually store the data inside the fixed memory. So where does this kind of fit in with our kind of overall architecture? So again, we've got our memory address register, our 12-bit register that stores our current memory address. And then we talked in the last episode about the eBank service and the eBank register, which is used to switch in and out banks of erasable memory. And then we also have the FBANK, which is a 5-bit register used to switch in and out fixed memory pages so that we can use different parts of our stored program for running the guidance computer. And then we've also got these FEXT or extended or superbank, which is used to add additional stored or fixed memory banks to the Apollo guidance computer as they try to shoehorn more and more capabilities into the platform as it evolved. What's interesting is if you look at some of the studies that were done for a potential Block 3 Apollo guidance computer, if the program had continued and additional improvements were to be made, a lot of this would have been reworked. And the S register increased in size, so you'd have sort of a continuous accessible memory space rather than having to switch banks in and out, which does make things a little bit more complicated, but it's what we have to work with. So, as I was talking about, we've got the FBank, which is a 5-bit register, and then we've got the FEXT, which is a 3-bit register. Now, what's interesting is even though that the FEXT is a 3-bit register, the Apollo guidance computer, as it was implemented, never actually used all of these additional extended banks. So even though there's 3 bits, most of them were never actually used in the Apollo guidance computer. Similar to the eBank, we've got these commands, the RBBK, control pulses, sorry, and the U2 BBK, which are basically when we're talking about these kind of both bank registers, which is both the eBank and the FBank. So there's a command that will, or a control pulse that will basically read the contents out to both write lines. And then we've also got write the contents of the adder into both banks. And then like the eBank, the FBank is a directly addressable register using memory address octal. This is actually should be 004. You can see XB4 here. And then also we've got the XB6 memory address 006 for both banks. One thing, and thanks again to Mike Stewart for pointing out, even though I showed this table, and this is a very, very useful table to kind of show what data is being written out onto which write lines for each of these directly accessible or addressable registers, you'll notice that when the eBank is written in or out as a direct addressable address or register, it actually writes to and from write lines 9, 10, and 11. However, if we're writing it through memory address 006 or the BBank register, the both bank, you can see that the eBank contents are actually written to write lines 1, 2, and 3. So I'll show that just as we go into the circuitry, the schematic in a few minutes, just how we had to sort of update that to make sure that this is reflected. But as we'll kind of see, we've got here that the fixed memory is divided into 64 banks for addressing, each bank storing 1K or 1024 words. However, only 36 banks, 00 through 43, were actually built into the guidance computer. The other banks, the other 28 banks, 44 through 77, could be added into the future. So we'll make some provisions if we ever do want to use this, but we'll be building it as kind of as close as we can to the actual computer as it was implemented. Now, one thing is we kind of talked about, okay, how does data get in and out of the eBank and FBank? Well, what about the super bank or the extended fixed bank? And this actually took a little bit of sleuthing, and I'm again, thanks again to Mike for pointing me in the right direction. But if you actually look at the I/O channels, and this is something we'll get to in subsequent videos when we start talking about the I/O subsystems for the guidance computer, is you have this channel 7, which is in this case it's showing here 1 bit, which probably makes sense because only 1 bit was ever really used, even though the memory map does include additional banks that were based on the idea that it would be 3 bits. But this is what basically says the high order bank, and it's an internal, in this case, lunar guidance computer. This document is reflecting the version of the Apollo guidance computer that was built into the lunar module. And so you have this additional, basically I/O channel that is being used to set the this FEXT register. So that kind of control logic as we bring data in and out of that will come when we start talking about I/O. But for now, at least we know where that data is coming in and out of. So that you can kind of, through a indirect method, write data in and out of the FEXT register. Basically, you have to use some of the channel commands. So you basically would write whatever data you were looking for out into the channel bit or pull data in from the channel bit or channel 7 in order to set the register contents. So once we get into address decoding, and so we talked a little bit about this in the last episode for the erasable memory, but as you can see, the address decoding for fixed memory is a bit more complex, right? So we've got a whole series of basically options where we can say, okay, if the address is the high bits in our S register are either bits 11 and 12, and one of the things we talked about is, well, the eBank doesn't really use these, right? So whenever 11 or 12, bit 11 or 12 is set to 0, so either 0, like both of them are set to 0, we'll be accessing erasable memory. So if they're not 0, we're accessing our fixed memory in one way, shape, or form. And so there's a bunch of kind of rules, like if bit 12 is 1 and bit 11 is 0, regardless of whatever is our contents of our FBank of our extended bank, we're basically just accessing the bits 1 through using bits 1 through 10 to address and access those elements of fixed of memory, which is our kind of what they call the fixed F memory, that these are always accessible. So basically address is 4000 octal to 5777 and octal 6000 to 7777. These are always addressable by the Apollo guidance computer. The high kind of, or sort of in this case, the low, because of the way the memory map is laid out. So 2000 to 3777. If FBank is set to 2, so 1, 0, we're accessing our fixed bank 2. If it's 1-1, we're accessing fixed bank 3. And then we've got a bunch of other combinations here. So if we have bit 12 is 0, bit 12 is 1, then basically we look at the FBANK to identify what FBANK we're actually going to use. So if it's 100, so that's 3, means we're or sorry, what or 100, which is 4, means we're accessing fixed bank 0 or sorry 4 and 5 and 6 and 7 and 10. You'll notice that these all count up in octal, and that's kind of how the memory map works. And then once we start getting further down in the memory, we can see like all these, we just ignore the contents of the extend bit register. And then, okay, if it's set to 0, we'll start accessing these kind of basically channel 0 through 3, what they call. Basically, if this is set to 0, we don't care what the contents of bits 5 or 6 are, which is actually bit 1 and 2 of our FEXT register. And so that's basically saying if this is a 0, 1, 2, or sorry, yeah, 0, 1, or 2, we're going to access the appropriate FEXT channel. And then we can see, anything beyond bank 44 was not actually built into the Apollo guidance computer, but they still have the memory mapping in order for us, if we ever wanted to add them, to allow us to do so. So let's kind of translate and move over into the electronics themselves of the S register. So how do we implement this? So first, I'll just kind of scroll over and talk a little bit about what I ended up doing in order to address that issue with the eBank, right? So now, originally we just had the 174LS157 selectors. We could select between either the contents of the sum or the adder, or we could bring in data from the write lines. What we've done now is I've added a second 74LS157, and depending on whether we're addressing the eBank register directly or the BBank both bank register, we will pick whether we load it off of our write lines 1, 2, and 3, or write lines 9, 10, and 11. So that fixes the one issue there. One other quick change that I've made to the erasable memory, and this is a couple of folks have provided this comment, is the type of memory that was used on or type of erasable memory that was used on the Apollo guidance computer is it's actually non-volatile. So that means that if you turn off the power, the RAM keeps its memory, right? So this was something that was used actually as a feature within the guidance computer, because the computer did take a lot of power. So there were a lot of times when it really wasn't needed. So when the lunar module had landed on the surface of the moon, well, they weren't going anywhere, so they didn't need the guidance computer up and running. So they could turn off the guidance computer while they were on the surface, and then when they were getting ready to leave, they could just turn the computer back on, and it would pick up where it had left off, because the RAM was non-volatile. So that's different from most computers people are familiar with today. Is you turn off your computer, anything in RAM is lost. So in order to kind of replicate that, I've added this basically supervisor chip, which provides battery backup. It'll also provide some additional features around reset and basically monitoring the voltage of the power supply, so that it can basically keep the computer reset until power reaches a certain threshold, and basically the electronics stabilize before it'll allow things to start running. And I may play around with it because it does have some, like, basically a low voltage detection and power supply kind of failure detection, which the real Apollo guidance computer had, right? So if there were power supply issues, it would generate alarms in order to reflect that concern. So maybe as we get further along and start looking at some of the alarm circuitry, we may take advantage of some of this to kind of replicate that. Anyway, back to the FBANK. and FEXT register. So what we have here is using 274 LS173s. We have our 5 bits. So unfortunately, we had to add one more to get that 5th bit because each of these are 4-bit registers. So we've got 2 of those to get our 5 bits. And then we've got our selectors similar to what we did on our eBank. So we can either load data in from the sum or the adder or from our write lines. The FBANK doesn't have that kind of dual mode that if you address it directly, it uses certain bit positions, and if you access it through both banks, it uses different ones. In the case of the FBANK, it's the same both ways. And then I've also got the additional 3 bits for the FEXT register. And right now we're going to bring that in from channel 7, bits 5, 6, and 7 when the time comes. I'm pretty sure it's bits 5, 6, and 7. I saw one other place where it's kind of referred to as 7, 8, and 9, but if you actually look at the memory map that we were just talking about, we can see the FEXT is 5, 6, and 7. So that's we'll kind of keep that consistent as we build the Apollo guidance computer. Now, when it comes to address decoding, this is where we can take advantage of some more modern techniques that the original engineers did not have access to. So in the original Apollo guidance computer, they actually had to build the address decode logic out of discrete gates. Now, as I kind of played around and tried to map that to the EPROMs we're going to be using for our fixed memory, the electronics, the kind of the decode logic can start getting pretty complicated, and the number of gates involved to actually build it start becoming pretty substantial. And so I'm going to take a bit of a shortcut, and we're actually going to use a 3rd EPROM to actually act as our decode or address decode. So this is basically we've got the inputs to our EPROM here. So we've got basically our various address lines, and these address lines come in from, you can see here, we'll actually pull S11 and S12 as 2 of our addresses. And then we'll pull the contents of these are basically the first 2. Then we've got our 5 bits coming in from our FEXT register. And then we've also got our additional 3 bits coming in from our FEXT register. So that provides kind of our address space of, within the EPROM. And then we'll have our output that will basically, so our outputs here of our EPROM, we'll use that to actually generate the appropriate address signals to bring in the right data out of the EPROMs that we'll actually use to store the program itself. So the way that I've kind of done this is I've used some 512K by 8-bit EPROMs. I was able to actually find a bunch of these surplus, and I just kind of like them because you've got a fairly wide address space, so you can use them for, in this case, not only storing quite a bit of data. So that's basically 64K times 8. So 2 chips is enough to replicate the capacity of the Apollo guidance computer. But the way that I've kind of implemented this is we've got our low 10 bits, just like we did on the erasable memory. And then basically everything beyond those kind of first 10 bits. So we've got our 8 bits here, and then we've got 8 and 9 here. So because it starts with 0, this is our 9th bit, and this is our 10th bit. So those are all the addresses we'll just generate directly from the S register. And then using this to kind of replicate the combinatorial logic to do the address decode, this will actually generate which page we're accessing, and from that we'll actually use that to generate the higher address lines. So address lines 11, 12, 13, 14, and 15, which will basically come from this decoder, so we can access the appropriate memory page within the EPROMs, and then those will be written out into our G register that we'll talk about or start talking about in our next episode. Similar to the eBank memory, there is kind of timing around, well, when should we actually write or make the data available to the G register. So the first is we've got this kind of OR gate, which is connected to our S11 and S12, because as we just talked about, if both of these are zero, then we're accessing erasable memory. If either one is a one or both of them is a one, then we're accessing fixed memory. So that's kind of one signal that we use in order to say, okay, when should we make the contents of our fixed memory available to our G register. And then there's also a timing signal. So you can see here, we actually AND it with our T07, and I'll show you the slide just in a moment. And then because it's, of course, the enable is low, we AND it or use an AND gate, and then bring that back to our basically output enable, which allows us to actually push data onto into the G register. So that is basically the electronics that will make up the FBANK and FEXT registers. And you can see, if I'll just flip back to the slide, that if we look at the timing, so I basically pulled this from the manual for the fixed memory timing, is they use this STBF signal, which is when the core rope memory would basically put data out onto the sense amplifiers, which is, you can see here, during the T07 pulse. So that kind of is all the components that will go together to make our S register. So I've got a picture here of it I'm building it right now. Of course, it's not complete, but you can see it's starting to come together. But we've got our full bill of materials. So we've got a total of 7 4-bit D-type registers. So this is for our S register, our eBank, our FBank, and our F extended or superbank. We've got a total of 4 74 LS157s. These are our selectors so that we can decide what input or what data we write into our registers. We've got 3 74 LS247 octal bus transceivers. So this is to basically manage the scenarios where we need to read data out of our registers and push them onto the right bus, and that's those basically those cases where we're writing data or reading data out of the FBank and eBank. This I meant to delete. There is no ALU or function generator, so I'll correct that on the final version of this. And then we've got our 2 static RAM chips that'll replicate our erasable memory. We've got 2 EPROMs. This will replicate our fixed memory, and then we've got this one additional EPROM, and that's our logic decode for our fixed memory. And then this is the supervisor chip, the MAX 704, that I'm going to be using. And then for all the glue logic to hold it together, we've got 1 74LS00, so that's a quad 2-input NAND gate. We've got 1 74LS04 hex inverter, 3 74LS02 quad 2-input NOR gates, 2 74LS11 tri 3-input AND gates, a 74LS32 quad 2-input OR gate, 2 74LS27 tri 3-input NOR gates, and a buffer that we of course use for our clock and reset. In this case, I'm only using 15 red LEDs, so I've got the 12 for the contents of the S register, and then I've got 3 that I'm using for the contents of the eBank. I'm probably going to play around because I will like to see what the contents of at least the FBank register. So you can see on these longer chips, longer boards that I've got created, I actually have a little bit of space for adding additional LEDs. Right now, I only have 4, so bank needs five. So I don't know if I'll use these or basically use one of these up here and solder a couple of LEDs in place of a chip and use some resistors to basically control the current through them and use that to actually display the contents of my FBANK register. Okay, so that's the S register and its associated eBank, FBank, and FEXT. In our next episode, we're going to start talking about our G register, which is our memory buffer. So that's how we get data into and out of memory. And as always, if you want to continue to see these videos and get notified when the next one comes out, click subscribe. And as always, as I'm going through this is a learning process for myself as well. So if you see any errors, mistakes, have any questions, please feel free to comment. I'm happy to answer any questions and make any corrections that you might identify. Anyway, until next time, thank you very much.